Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. My name is Karen Strauss, and it's my pleasure to introduce Professor Kevin Fu. Kevin almost needs no introduction. He's a regular here at MSR, but he's an associate professor at UMass Amherst. He's an expert in security and privacy and embedded devices. He has won many awards, including the TR35 and the Sloan Fellowship. And with no more ado, Kevin.
Right. Thank you, Karen. All right, and it's all, of course, because of having great students. So I have Negin here today, and Jeremy also has co-authored papers with me in the past. So it's you can't have good research without the great students. So I think I have the mic here. Okay, so what is this talk about? I normally work in security and privacy, but about 6 years ago, we ran into a problem whereby we were trying to get cryptography to run well on an RFID-scale device. We actually have one here today. So my model, it's a programmable RFID tag, no batteries, takes all of its energy from radio waves essentially, and performs computation, sensing, and then uploads that data. But we couldn't get the crypto to work well, and the bottleneck was we couldn't store anything because the flash memory wouldn't work at low voltage. So this kind of set us down a path of, okay, let's think more about the platform and rethink abstractions, because if we can't get basic things like storage to work, then there's no hope for the more interesting, higher layer to me, issues of things like cryptography and just applications in general. So this talk is going to be covering sort of two different domains of non-volatile storage on these embedded devices, typically extremely low power. We're not talking ARM processor. To me, that's like a power plant. We're talking much lower power than ARM for this talk. And this is based on two papers. First, we'll talk about Mementos, which was published at ASPLOS earlier this year. And it's essentially a set of compiler optimizations to make programs run well on a platform like that, where the platform might reboot, say, every 100 milliseconds because of energy loss, because it just can't get enough energy from harvesting. And then the second half of the talk will be about some research that Negin had led, and it's about how to write to flash memory at voltages that the manufacturer says don't. And we'll show how we can do that well and save quite a large amount of power. Okay. And feel free to interrupt with any questions. We can always go down a different pathway if you find a certain topic of more interest than another. Just a little bit of motivation and sort of to bring us back to some fundamentals. In the 1980s, Mark Weiser was talking about ubiquitous computing. This was a term he liked to use. And he would talk about that the most powerful things are those that are effectively invisible when you're using them. You could almost argue that phones are getting pretty close to being invisible, because sometimes you forget it's even in your pocket, right? I'm sure we're going to hear something ring today, so that's ubiquitous. But when a batteryless invisible computer comes to be, then you run into a fairly simple problem, or excuse me, a simple problem with profound implications, and that is the thing reboots a lot. When you take away batteries, you no longer have that safety buffer of energy. And so Mementos is our way of addressing how to get programs to run well when you reboot a lot. So we had sort of a three-step approach to getting things done. And that is, first we took this emerging platform, which Jeremy has there. Again, it's a batteryless, programmable, effectively an RFID tag. And we're going to try to make it more robust. So to make this programmable RFID tag more robust, we first worked on getting a compiler to do good optimization, and also doing trace-driven simulation. Because if you just go and try to build this on hardware, you might find you've just built a wonderful piece of software that has no use. So the nice thing about a simulator is you can very quickly remove things that would not have worked on hardware, and get a pretty good sense of how it would perform on hardware. So here's a picture of one of the earlier devices. This is the tag that we're starting to actually manufacture. It's based on the Intel WISP. We call this the UMass Moo, only because we think it looks like a longhorn steer. But it's a programmable RFID tag, no battery, and in fact all of its energy is stored right here in this 10 microfarad capacitor. And I'm thinking they might want me to use this laser pointer instead of walking. So this little 10 microfarad capacitor is the only buffer we have for energy. The whole microcontroller runs off that thing, and it gets filled up with this antenna. This dipole antenna does all the energy harvesting from RF, and it also does the digital communication, so the wireless communication back to whoever's interrogating it. To give you a perspective of just how much energy that is, it's about 5-6 orders of magnitude less energy than you could store in a AA battery. So imagine trying to compute with 5 or 6 orders of magnitude less energy than a AA. That's what we're doing. Okay, so here's some of the problems you're going to run into immediately when you try to compute on these extremely small-scale devices. First, here's an actual trace. We remove the units to make it to focus in on one thing. What do you think of when you see this line going up and down a lot? What word might come to mind statistically? Does it look constant to you? No, this is highly variable. So this is a voltage trace. And the one thing to take away is we have a highly unpredictable, highly variable voltage supply. The exact wrong thing you ever want to give a microprocessor or any digital system. So we're somehow going to have to cope with that. So the coping mechanism is a small capacitor to help us smooth things out. Problem is with a small capacitor, when it drains, think of it as your water tower draining. You don't have water anymore. So in this case, instead of just not getting clean, we just don't compute. And when we don't compute, well, we have reboots. And it's typically on the order of 100 to a few hundred milliseconds before we have a reboot. So the lead graduate student on this, Ben Ransford, I asked him to plot the reboots. And I guess he was creative that day. So he decided to plot. This is an actual plot of how often the device in Jeremy's hand there was rebooting. And this was when it was directly next to a 1-watt transmitting RFID reader. That is, it's sort of getting the most power it could possibly get, and yet it was still rebooting. It's hard to compute like that. And so we liken this to the idea of having a small child. So imagine you're trying to write your paper, and you have a small child who's trying to get your attention and just starts throwing this beach ball around your head. And every time the child interrupts your thoughts, you forget what you're doing, and you have to start over writing your paper. You're never going to get done with your paper, right? And all the authors, by the way, have toddlers. That's what restraints are for. No, parallelism. I don't know. We eventually got done. But it can be hard to get done when you have constant interruptions. So we call this a Sisyphean task. So in the great myths of the classic era, poor Sisyphus had to roll a rock up the hill, and every time he got near the top, he dropped it, and you have to start over. So you can imagine your computation, you're rolling it up the hill. Every time you get almost done, you drop it, and you have to start all over because you lost your energy. So we're trying to avoid that. We're trying to figure out how to get these long-running tasks to complete in short bursts. So before we get into our approach, I'll just give you an idea of how it's done today. This is not a new problem. But it is a different way about thinking of the problem. So typically the industry will just constrain the problem so you don't have to worry about reboots. So this is a contactless smart card. Has anyone been on the London system? Yeah, so this is the London Oyster card they use for payments. And there's a pretty standard 300 milliseconds is the golden rule that says anything you do, whether it be crypto or communication, needs to finish in 300 milliseconds. Otherwise, there's sort of this exponential increase in passenger frustration. As they're swiping the card, they'll get angry at it, and they don't understand why it's not working. So they always finish in 300 milliseconds. And if your computation takes more than 300 milliseconds, they say, well, you shouldn't be doing that in the first place. So we think that's a silly idea for the general computation. And so Mementos is going to relax this constraint so we can make general purpose computation feasible. Of course, it may take many, many reboots. So in the typical world of energy, you're going to be given a relatively constant voltage, which is, if you integrate that, that's infinite energy. over time. But in the real world of our world, these are real traces over 40 seconds each. Your voltage is going to vary, and it's going to vary quite a bit. These three different traces were of a student holding this tag, harvesting energy, and doing the exact same thing each of the 3 times, but you get a radically different voltage trace. So we have to be able to cope with this variability. So the approach to dealing with a variable voltage supply and all these constant reboots is fairly straightforward. It's checkpointing, and I think many of you are probably aware of the checkpointing work. There's tons of research on checkpointing, especially in the last few decades for things like grid computing, which I guess is now called cloud computing. So here's a trace of our voltage as we're about to die. So 1.8 volts up here is where our particular microcontroller will start to fail. And so that's the death point right there. And this is actually part of an exponential decay, but we're kind of zoomed in, so it looks linear. But imagine that your computation is rolling along, and there's some region as you're getting close to death where you think, well, that's a good place to checkpoint what you're doing. So that's what we do. As the computation comes along, we checkpoint it before we die. And at that point, we sort of go into a hibernation state as we're harvesting energy. When we get enough headroom, when we get enough energy, we can start over again, do a restoration, and then continue our computation. So that's the easy part. Question?
Just a quick question before you get back to motivation. Why don't they just increase the capacitor capacity a bit?
Good question. So we've tried increasing, actually Jeremy increased the capacitor with a supercapacitor. You can increase the capacity. The problem is the voltage on a capacitor is proportional to how much energy is inside it. And basically, if you put, say, a supercap on here, it might take you 24 hours to charge before it responds. So there's a trade-off between responsiveness, and we want sort of for us, we kind of want 1 second or less response time versus this sort of insurance policy of how to cope with energy outages.
So you need multiple capacitors instead of the cost.
You could have a bank of capacitors.
That increases the cost.
It increases the cost and complexity. So for most of our work, we focus on sort of the fundamental case of a single small capacitor. And there are a lot of fun tricks you can do to use supercaps, but it always involves something like hybrid energy harvesting, adding solar panels, other energy sources, so far in what we've found. Yes?
Very good question. To do the checkpointing, you need to know, like, at what point in the future you have to do the checkpointing. Like, it has to be predictable, right? What if something happens out of the blue and you haven't accounted for it and then you lose data?
So this is precisely why that's the hard part of the problem that we're going to try to address in the next few slides. The easy part is knowing we need to do checkpoints. The hard part is knowing when to checkpoint and what to checkpoint. Okay. So we're going to use a running example of a CRC check as our application. It might sound a little silly, but believe it or not, CRCs are still pretty hard to do on one of these platforms just because they're so low power. So it takes just slightly more than half a second to run this code, and it takes about 575,000 CPU cycles. The interesting thing to note is that we reboot about every 100 milliseconds, so we're never going to get done with this very simple CRC without at least checkpointing. And the next question is, what are the best checkpoint strategies so that we can get pretty close to some kind of minimal running time? So that's sort of what was driving us to get the programs to run well. So let me give you an overview, a programmer's overview of how would you use our system, Mementos, to make your code run. You can write your code in C. Actually, you can write it in any language that LLVM supports. So we use the LLVM compiler instead of GCC. It's a little more modular, easier to modify. So you write your code, and you'll need to choose certain parameters and these parameters will help you determine the efficacy of your checkpoint strategy. Now, choosing the parameters is what's done by Mementos. So what Mementos does is it instruments your code, its intermediate representation during the compilation stage. It instruments it with energy checks. It becomes energy aware. It has a notion of what is a capacitor and how it behaves in different conditions. And then we've built a simulator. But it's not just any old simulator, it's a trace-driven simulator. It actually takes as input voltage measurements from an oscilloscope so we can see how the program would behave in a realistic scenario. It makes it reproducible, and so you can actually learn from it. The simulator helps us pick these parameters so that we can dump it onto hardware and see it actually run. Okay, so that's the basic idea of what Mementos is doing inside the compiler and inside the simulator. The next piece is understanding the heuristics we use to actually instrument code. So I said there were two things we have to solve. We need to figure out when to checkpoint and what to checkpoint. So this is going to answer the when to checkpoint question. So here's your code. What's a good place to checkpoint? You might choose to checkpoint at the end of a loop latch. Seems to meet some intuitive sense because you've just finished some important computation, so there's probably something to save in your registers. So that seems like a logical place to do it. Or maybe after a function call return, because in traditional stack-oriented machines, if you do a function call, you push all your arguments on the stack, you do your work, you come back, and you pop everything off. So we would expect to have a local minima in our stack, and therefore much less state to have to checkpoint in the first place. We have a number of other instrumentation strategies, some involving timers, and that's in the paper. But I think these two should give you a sense of how we're going to decide where and when we're allowed to have checkpoints. In other words, we're not going to do a checkpoint right in the middle because we don't think that's logical. Okay. The next thing we did was we simplified the problem of knowing. Let me back up a moment. That was static time. That was compile time where we decide where to put potential checkpoints. At runtime, we need to know, okay, we've entered an era where we could do a checkpoint. Should we actually do a checkpoint? And to do that, we pick a threshold. And if our voltage supply has dipped below this threshold, we say, all right, let's do that checkpoint. So as we get to death, this is a happy talk. Imagine you have your checkpoint, and don't forget, it's not instantaneous. Your checkpoint does take time. You could checkpoint early. You could be very conservative. Maybe you're a fiscal conservative, and you'll do this. But then you find that you're just wasting energy. Because if you think about it for a moment, if you're consistently checkpointing early, there's that little tail. And what that means is every single time you run your program, you're going to have a much shorter run. And you're going to end up having many, many more runs. And so you're going to be paying a lot more energy on your restoration checkpoints because you're doing more of them. On the other hand, if you were to checkpoint a little bit too late, like my little brother, then you're probably just going to have to start over or give it to your older brother processor to finish. So you don't want to miss that final point. So really what you want is this Goldilocks checkpoint area. You want to do it right before there. You do this sort of flatlining right before you die. Have the checkpoint happen. And it's pretty tricky to locate, but if you make certain assumptions about how your checkpointing process works, you can still pick a V threshold on the conservative side, such that it's very unlikely to die without having checkpointed. Oh, yes.
So you're assuming, and I assume this is probably correct almost all the time, the checkpoint is really expensive. If checkpoint were really cheap, you just do it all the time.
If checkpoints were cheap, we would do it all the time.
Can your code detect, for this particular program, the checkpoint is just this tiny CRC that just is the checkpoint?
Correct. So there's a huge amount of optimization that I think can still be done. For instance, later on, I'll just say now, it'd be nice to have more dynamic understanding of the program. So right now, we just assume sort of a worst case scenario. We checkpoint all registers and all RAM because RAM is small. The earlier version only had 256 bytes of RAM. So we would just checkpoint everything. But as RAM grows on these devices, we're going to have to be smarter, think about compression, think about more of those interesting things. But writing to flash memory is a very expensive operation on this device because you have to jack the voltage up in order for it to run well.
Have you tried choosing V threshold dynamically? So you lower it until things misbehave and then you make it up until you're too conservative?
So we haven't done anything dynamic yet. And I think that's sort of a right next step. Right now we said we need to simplify the problem so we can at least make it solvable. Okay. So one more question.
So you have this V threshold set, and then you probably have like a monitoring unit that monitors the voltage, and as soon as it gets V threshold, it does that. So what about the overhead of the monitoring?
Okay.
How often do you have to
I do have a slide that talks about the cost of the monitoring. It's going to be, if you can wait, it'll be probably 10 slides later. Okay, but there is a significant cost to monitoring, so you also don't want to do that just all the time. So already you can see it's pretty hard to do. Let me just tell you about other things that make it even harder. Our flash memory has no flash translation layer. We got to manage the whole thing on our own. You filled up your flash and you need to erase a segment of flash before you can write to just one word of it. You got to do that yourself. And by the way, you're checkpointing your registers, so you can't use any registers to make decisions. It's kind of circular thinking, right? So it's really hard to write code when you're trying to checkpoint the system itself. You can't just overwrite arbitrary things in flash memory. That's not how it generally behaves. It's very painful. I feel sorry for Ben because this was a huge amount of development. Let me just tell you about some of the debugging. I believe he was saying, and you can correct me if I'm wrong, I believe he told me he actually implemented Manchester encoding over the LED for debugging because it's sort of, to me, it's sort of equivalent to printf debugging. It's really hard to debug these things when there's no user interface. And moreover, if you touch it with a wire, you might actually disturb its performance. So it's very hard to work with these devices. Fickle harvesting, those first 3 slides, I showed you these 3 voltage traces. It's completely not reproducible. If you want to run an experiment and have a colleague at another university replicate it, forget it because it's a different humidity over there. So that's why we focus on making these reproducible.
If you can't use the registers to make decisions, how do you make decisions?
You just need to be careful, and very careful. And this means you lose a lot of the abstractions that we take for granted. Right? Okay. So to bring back a little bit of reproducibility and science to all this, we decided we needed to have a trace-driven simulator. If we couldn't get people to reproduce the results, then what's the point? So this is based on a tool called MSP-Sim. It's already been out there. Ben and others augmented it to be to actually capture notions of energy. So literally what he did was he took a scalpel, he cut off the front end of our little device, the energy harvesting front end, would measure the voltage coming out of it, and then that voltage would be fed into our software, the simulated capacitor. So it's sort of first order physics approximation of how capacitors behave under different voltages. And then we throw that into the simulator, and this causes the simulator to have a notion of when to fail, when to reboot, when there's not enough voltage. Okay. Again, it's sort of physics 101. There are all sorts of weird nonlinearities when you're dealing with capacitors. But we did validate this. So we actually measured the end-to-end power consumption, energy consumption rather, in order to verify whether our simulator was pretty good. And you can see the paper if you want to know more about that accuracy. Okay, so you've got this program that our handy-dandy Mementos edition has instrumented with energy checks. Now we'd like to see how it actually performs in the simulator. So the simulator takes as input 2 things, that executable, the instrumented executable, and a voltage trace. This allows it to be reproducible because you can give the voltage trace to somebody else and they can go run it. The output is a little more complicated. The simulator is going to tell you in the ideal world, here's how many reboots it's going to take to finish. Here's how many CPU cycles, and total wall time, and also an execution trace so you can go back and see why things failed. To give you an idea of what it looks like, here's a real trace that's been annotated a bit with illustration. The blue down there on the bottom represents the energy harvesting front end. When we harvest energy, it's fairly low voltage, and then we use some special circuitry. It's called a charge pump in order to get it to be a higher voltage. And we put that into that 10 microfarad capacitor. So you can see it takes about 3,000 microseconds until we get up to about 4 volts. Suddenly our hardware turns on and starts to compute. And we're sliding down that voltage. As we compute, the voltage on the capacitor is going down until we fail at the red mark where we do a checkpoint right before failure. And then the little green dot up there represents a restoration. So you can see it takes many reboot cycles to get this CRC check done. Okay, so the simulation is great, but what would be better is if our simulator could tell us not only how our program performs, but how good could it perform. So during the rebuttal process, we decided we needed to implement this, what we called an oracle. It essentially, with certain assumptions about the workload, it essentially finds the optimal way you could ever possibly hope to do checkpointing. It doesn't necessarily imply that you could reach this optimal. It doesn't even tell you the strategy to do, but it says here's the best thing any strategy could do. You can think of it as sort of a binary search on our threshold voltage. So we're assuming that the only knob we have is the threshold. And with this knob, we need to know where to turn it. And we need to pick that knob to be static because we don't yet have any dynamic control. So the first thing we do is we run the program at a very low threshold, and of course we're going to die. And we keep bringing that threshold up until we don't die, and then we think, oh, well, let's see if we can inch it back a little bit more. And so we do a binary search on those little deltas until we can finally zero in on what we consider to be a pretty good threshold voltage where we don't expect to get any closer to death and still survive. So that's how our oracle works. The oracle then outputs what was this running time. So we can use that as sort of a benchmark of how good are we. All right, hooray. Okay, so how did we actually do this? At the high level, again, Mementos is splitting these computations into chunks. At compile time, it tells you sort of where the edges are of your plate tectonic computations. And then at runtime, it tells you sort of which ones are actually going to cause interesting events. And we're using the CRC example. We've also done some elliptic curve, RSA, but CRC is sort of the simplest example to demonstrate how the thing works. Unfortunately, there's not a lot of other code out there to compare against. Nobody else wanted to go through this pain. I can understand why. So what we do is we compare against our checkpoint oracle. So at least we know how close we are to ideal. To give you an idea of just scale, Mementos itself is only about 2 kilobytes. And 1 kilobyte of our flash memory is reserved for the checkpoints themselves. We have basically banks of checkpoints, and it's kind of tricky to swap between them because we don't want to erase a checkpoint before we know our next checkpoint is actually set. It's kind of tricky to do when you don't have full control of your registers. This is answering your question about why don't you just say constantly monitor. To do monitoring of the voltage supply takes about 0.1 milliseconds. This is mostly because of the analog digital to digital converter. This is a fairly significant cost. It translates into a large energy cost. It's pretty close to a flash write. So we don't just want to do it all the time. But then the program in itself only takes about 4 milliseconds, and the restoration 2 milliseconds. Okay. One other thing to point out. A question we often get is, why don't you just use TinyOS? And believe me, we wanted to use TinyOS. So TinyOS is this operating system, or library rather, for sensor motes. And the problem we ran into is it took about 100 milliseconds to boot TinyOS, isn't that right? And that was after you optimized it, correct? So if you optimize TinyOS, you can get it to boot up in about 100 milliseconds. And we needed 2. So we much prefer the 2 over 100. Otherwise, we'd never get anything done. We'd boot up and we'd say goodbye. Okay, so let's take a look at this CRC test case. And we ran it through our oracle using this energy trace. So we just randomly picked this guy. In the paper, we have, I think, on the order of 10 different traces to exercise different characteristics. And the oracle told us, it'd take you about 4 seconds. And the best you could ever hope for is 14 reboots. And by the way, we recommend, based on our oracle, pick a threshold of 2.35 volts. Just pick that. Again, not dynamic, static, and that's what you should get. So we ran this against the simulator with our actual checkpoint strategy because we can't just pick any strategy. We have to pick something a compiler knows how to do. And we were able to finish in about 16 reboots in slightly more than 6 milliseconds. And that was with a threshold of 2.6 volts. So, it's not as good as ideal, but it's getting pretty close. And that's sort of where we are today. And I can just point out, so sometimes you read a systems paper and you ask, is this a paper about improving performance or is it about better semantics? And this is definitely not about better performance. Here it's about semantics. We're trying to get programs to actually run. The status quo is programs don't run. So at least we get them to run, and the penalty is about 10x. Is pretty typical, but at least we can get them to complete if there's a pathway to completion. So you've already seen the one with Mementos. If you don't have any kind of checkpointing strategy, you can see you've got these Sisyphean tasks. You roll your computations up the hill and you keep dropping it and you'll never finish. There's tons of related work in this space in RFID-scale devices. Especially, I'll point you to a paper by Michael Buettner at UW, Dewdrop at NSDI. He has a different approach to dealing with energy constraints. They essentially have a scheduler, and the scheduler will look at your energy levels and decide which task to run based on how much energy is left. So if you're very low on energy, you might only do a quick task. In our work, we're thinking that we have a single task, so we don't really have a choice to do any scheduling. And again, checkpointing has a rich history. I usually think of things like Condor from, I think that was, the early 80s? Or was that the early 90s? But from Wisconsin on grid computing, because if you want to do migration of your computation, you need to checkpoint it. So there's a lot of interesting things you can borrow from the checkpointing literature of yore. As Jay mentioned, why not do dynamic? We think it'd be really cool to have some sort of dynamic decision making. We just chose to solve the simpler problem first. It'd be a great, I think, extension. And I would hope you could do better, but it's not obvious to me if dynamic will actually make it better. Because anytime you need to make decisions, it's going to cost you CPU, and it might actually make it worse if you miss a deadline. So it's not clear if it'll work. We're looking into all sorts of other kinds of non-volatile memories, phase change, ferroelectric RAM. Some of these may make it a lot easier to do. And it's still yet to be seen. We were originally doing some compressed checkpoints. But as you can imagine, if you don't have full access to your registers, it's really hard to write compression code. So we decided not to do that. Actually, I think Ben said, please, do I have to do this? And I said, OK, we'll wait for the next time. All right, and we do have a platform actually now that we're selling. We're selling this guy for research purposes. There's my model again. Thank you, Jeremy, or Vanna. If you'd like to play with that or have one, come talk to me later. So this is sort of the, checkpoint of my first half of the talk. It's a good loop latch. Hopefully I'm not going to repeat. Or should I just start over? No. So Mementos is all about energy-aware checkpoints to help these batteryless devices get long-running things done. It won't necessarily get done quickly, but it'll at least get done. And it's using the LLVM compiler optimization passes to make this possible, trace-driven simulators so that you don't have to do it on hardware, find out that it doesn't work anyway. You can do it in software first before you get into the nitty-gritty of circuits. And the applications, there are all sorts of fun little things. We usually think of crypto and implantable medical devices, but I'm working with one evolutionary biologist who wants to use some of this for insect-scale tracking. So we recently were talking with experts from Cornell who are microsurgeons for crickets to be able to implant these inside crickets for tracking. But I'm not sure if that's going to work out. It'd be interesting if it does. So that's a checkpoint, but I think there's a question before
I just want to sort of clarify my understanding, because it sounds like, as far as the threshold voltage goes, you do a lot of work to compute the optimal perfect threshold voltage, and then add 10% because you're working with the real world.
Roughly.
Okay.
And there are other constraints, such as you can't just buy a voltage regulator for any old voltage you want. So there's certain manufacturing constraints. Discrete choices available. Okay. So any other questions before moving forward? All right. Okay. So the next thing I'm going to do is talk about some work that Negin led over the past couple years. And it all relates to getting flash memory to work well, saving potentially upwards 30 to 50% of the energy by basically violating abstractions. So we're going to violate abstractions with glee and try to make things still work. So big data, right? So here's the typical picture you see of a data center. and you think about massive amounts of storage and making those run using fewer joules of energy. The kinds of things we're going to care about, though, are if you take a look at our doctored photo, up there in the ceiling, you'll see a smoke detector. And that smoke detector has flash memory inside of it. Does anyone know why a smoke detector has flash memory?
Insurance companies?
Yes. Why do you think the insurance company... Actually, it's to use against insurance companies. Let me explain. So I recently went to a teardown of these devices, and the manufacturers said the reason that there's flash memory in their smoke detector is that, let's say your house burns down, and your insurance agent or your insurance company goes to the manufacturer saying, well, obviously your smoke detector failed, we're going to sue you. Smoke detector company says, let me see this smoke detector. Let me hit a few buttons, take a look. Oh, according to the flash memory, you never hit the test button. That means you're obviously an irresponsible homeowner, and I think you're the one liable. So they actually use the flash memory against the insurance companies and against the homeowners for liability. So it's legal reasons. Anyhow, there's flash memory inside there, and there's flash memory in a bunch of other very low power, typically battery-powered devices. I like to call them boring high-volume devices. So thermostats, smoke detectors, implantable devices are a little more exciting. Toll weight transponders, kind of boring stuff. But there is a lot of it. So there's over 10 billion in sales of these kinds of things each year in the US alone. Now, there's also flash memory in this thing called solid-state drives, and I know many people are excited about that. We're talking about things much deeper, smaller scale. Some of the things I'm going to talk about might apply to solid-state drives, but in the future. But right now, the price points are not very good to making this applicable to solid-state drives. Okay, so let's focus in on the smoke detector. If you crack it open, you're going to find a microcontroller. This one happens to be from Microchip, and it's got 8 kilobytes of embedded flash memory. And the interesting thing in the spec for the microcontroller is it tells you could run this at, say, 2.2 volts, or you could run it at 4.5 volts. And this gets interesting from a power consumption perspective because power consumption is proportional with V squared. So if you run the thing at a high voltage, it's not just linearly worse, it's quadratically worse. So let's think about how a manufacturer would use this in deciding what voltage to set. So in the ideal world, you can imagine you have this single chip that contains your CPU and your flash memory, and it's got 2 pins, the 2 different voltages. This allows you to scale your energy proportional with the workload. If you're not using your flash memory, you just don't bother using the 4.5 volts. If you are using the flash memory all the time, well, okay, sure, you're going to burn up a lot of energy, but you can dynamically scale it. Unfortunately, in the real world, what happens is energy is proportional to the worst case, no matter what you're doing. And the reason why is it's very expensive to put extra pins on a chip. So there's typically just 1 pin. You get to pick 1 voltage to rule them all. So if your CPU needs a low voltage to run and your flash needs a really high voltage, the manufacturer is going to pick the high voltage. Whether or not they use the flash memory, they're going to set it to a high voltage because they might need to use the flash memory. So we're going to try to make these chips behave more in the energy proportional world, even though we're actually running in the world where we have to pick a single voltage to work for everybody. And we're going to do that by violating specs and violating abstractions, but still bringing back reliability of our storage. So we're going to try to recover that wasted energy. Okay, so our approach is strictly software-based. So the cool thing is you can make some software abstractions in how you interact with the microcontroller, and it has this strange interplay with the physics of flash memory such that you can then save power. It makes no sense why it should save power strictly from a software perspective, but if you think of the bigger system, we'll show you soon about why we can save power. Okay, a little bit more about the state of the art. I've already told you the way things are done today is a manufacturer will pick the highest voltage because it's just the easiest thing to do, but then your device won't last as long, it'll use up the battery more quickly. The other approach, if you have a lot of money, is you just add hardware. So you could do sort of a poor man's discrete voltage scaling. That is, you can on the fly change your voltage. Unfortunately, this does require circuitry. And in high volume, low profit margin devices, they really don't want to spend 10 cents on even a couple transistors. So this is something that's generally avoided. And then I like to poke fun at Josh Smith. He was at Intel, now he's at UW. Our original motivation for this was he gave us one of his WISP tags, this programmable RFID, and we were going to write to flash memory, and he said, oh, you can't write to flash. There's flash memory there, but you can't write to it because we set the voltage too low. So they literally just disabled the flash memory. And we wanted to get it to work, so we wrote to it at the voltage we had, not the voltage we wanted. All right. And this picture should start to look pretty familiar. Okay, so the basic idea here is your standard engineering trade-off. We're going to run the thing at a very low voltage. We might get some errors. And we're going to need an error correction routine. And we need to know, well, is that error correction going to cost so much that it makes the savings not worthwhile, or not? Now, the good news is, I'll give away the ending, we can actually save more than we need to spend to do the correction on almost all workloads that we've encountered. Okay. So let's go back to a little more inspiration. Who used a punch card? You're proud of it? No. Okay. So in 1982, Revester and Shamir had this cute paper they called WITs. They called them write once bits. So this was back in the day where write once memories were fairly common. WOMs, for instance. You could flip a bit once in a direction, but you couldn't flip the bit backwards. So it was very much like a punch card, but electronic. And they figured out a clever coding scheme where they could make the memory rewritable by actually having sort of the next write be sort of a superset of the previous write. And they would trade off capacity with rewrite capability. So we took a look at that work and we thought, well, what if we sort of write to these write once bits sort of halfway? So this is where our Half-Wits work comes in. And let me tell you about just one example of how you might use this approach to write to Half-Wits. So we're using NOR flash memory. And in NOR flash memory, all bits are born as 1. They're all equal. And let's say you want to write a value to that memory where the 2 least significant bits are 0. Seems like a pretty simple operation. But if you're doing it at a low voltage, you might get some errors. The bit flip might not actually happen. So imagine that you do the write and the least significant bit does not flip. That is an error, and we'll have to correct for that. All right, so that's the bad news. The good news is this is what you call a Z-channel. So it's got these asymmetric probabilities of failure. So if you're trying to write a 0, there's a probability p that it will fail. But if you're trying to write a 1, it's never going to fail because they're born as 1s. So we're going to be able to exploit some of these asymmetries to get better energy consumption.
Is this independent per attempt of the same bit?
No. Yeah, this is where it gets interesting. So there are a whole bunch of different factors you might consider. And so Negin did all the experiments on this and all the experimental setups. We considered a bunch of different things. The ones at the bottom I'm not going to talk about because we have found no evidence that they actually influence any of the probability of error. But we will talk about the first 3 factors that influence errors before we get into our approach. We got one obligatory eye candy picture. You always need one of these in any talk involving electronics. We now have a digital power supply. This is kind of error prone, right? If you accidentally bump it, the voltage changes. But Negin can tell you more about this setup. This is her beautiful setup here. And we're running at 1.813 volts at the moment. And we're testing that platform with a second device to monitor it, how well it's performing and actually how much energy it's using. Okay, so let's get to the data on just how the voltage affects the error rate. It should be obvious that we're going to get errors. The question is, what does that error distribution look like? So here's a chip that was designed to work at 2.8 volts, I believe, right? Where is it? 2.2 volts, sorry. 2.2 volts. And you can see as you're edging your way down, there's sort of this cliff where suddenly a whole bunch of errors pop up. And so this was in one microcontroller. So there's a second microcontroller we had that was the exact same model, and it had a radically different cliff. So there, the error started around 1.92 volts. So variability, again, comes into the picture because of process variation. If you start looking at other microcontrollers of different families of microcontrollers from the same manufacturer, you're going to get different curves, different times of failure. So all we know is that there will exist a cliff. We don't know exactly where that cliff is, but we do know there are pretty big safety margins built in to the manufacturing. So anything above the cliff is wasted energy, basically. One other thing that I consider sort of just a confirmation of what we would expect is that Hamming weight is directly influencing our energy, our probability of error. So basically, if you have a lot of zeros, you're going to have a higher probability of error. And it just makes sense because flipping from a 1 to a 0, there is a probability of error. Not flipping, or writing a 1 involves no change, so there should be no error.
Are these probabilities for the individual bits or for the whole byte or whatever?
For the whole byte. So this is the Hamming weight of how many zeros are in it. So if we have, how many ones are in it. So if we have all zeros, all 8 zeros in a byte, it looks like about, was that 80, near 90% chance of some error. Some error in the byte, in the back.
Do you assume you're writing a block structured file system or something? You only write to the end of it? You never change?
Oh, we have no file system. So this is raw. This is raw access. There's no flash translation layer.
You're not going to go back and change a bit.
Oh, so we are going to do something very much like that. This is just observational data, trying to figure out how the raw flash memory behaves in strange voltage conditions or strange conditions. This happened to be at, I think, is it 1.9 volts? 1.8? Yeah, 1.8 volts. Another factor to worry about is wear out. I always thought that as you wear out your flash memory, I always thought that, well, it just gets crappier. But I guess that's not a scientific term. So what Negin has done here is we had 3 different areas of flash memory, blocks. It's very small. These microcontrollers don't have a lot of memory. And we artificially wore out through several read, erase, write cycles the midsection. So that's more often used. And then we wrote a bit pattern, and we checked to see what kind of error rate we were getting. So what's interesting is, so the lighter color indicates high errors. And what's interesting to me is that the midsection actually has fewer errors. So this tells you the more you wear out your flash memory, the less likely you're going to get an error. It was counterintuitive to me at first, but then I realized, wait a minute, it makes perfect sense because what does wear out really mean? Wear out means you're changing the bias from bias to 1 to bias to 0. So the more your flash memory is wearing out, the more likely, or the easier it is to get it to change to the 0 state. It also means it's harder to get back to the 1 state. So that's why erases get harder. But this is, to me, it was counterintuitive. Sure.
It looks linear, but shouldn't it be binomial? Because the more zeros.
Megan, do you want to take a stab at that?
So in each of those you have, you have 6 zeros or 7 zeros, so why shouldn't it be linear?
But it seems like, maybe I'm misinterpreting error rate. Isn't this the probability that at least 1 bit is wrong? So shouldn't it, when you have 2 bits you could get wrong, shouldn't it double and then shouldn't be exponential? Because the probability that the probability that at least 1 fails. Anyway, well, I guess
I have to think about that. I'm not sure. The other problem is, I mean, you could have an exponential and we might just be in the portion that looks linear. This, to me, it just sort of confirms that, yeah, the more zeros, the more errors.
To look at that, you have to turn the graph upside down, approaching the 100% error rate. not
All sorts of fun and tricks you can do with graphs. Okay. All right. Well, there's one other property I want to talk about, and that's sort of the most important one. And that is, I didn't know at first that flash memory has an accumulative behavior. The way flash memory works is it represents zeros and ones by how much charge is in the cell. And so if you attempt to do a write to flash memory and you fail to actually flip a bit, you've actually partially succeeded. You've got a little bit of charge to go into that flash cell. So the next time you try to do a write, it's going to be a lot easier to do because there's already a little bit of charge there. And that's the primary property we're going to exploit with our software abstractions to reduce the power consumption, to let things run at a very low voltage, and build a coping mechanism for when we do accidentally run into an error. So I'm going to skip a little bit forward to I don't think we need to talk too much about the model to understand how this is going to work. Oh, was that a question? No. But I'll just talk about some of the design goals. So we want the energy consumption. We want to minimize that. We also want to minimize error rate. And delay is also important because if you don't have a predictable amount of time before your data can be written, makes it a lot harder for the system developer. Of course, you might not be able to get all three at once. But let's talk about three different approaches and how they affect these different minimizations. So we tried three different approaches to deal with errors at low voltage. The first one we call in-place writes. This is where you can imagine you do a write to some location and you just have a feedback loop. You keep writing to it until it sticks. The second one, multiple place writes, is we're writing a value to one location and then we write the same value to a second location. Now there might be an error, but because the errors are this Z-channel kind of error, we never get errors in zero. If we ever see a 0, we know it's a proper 0. If we ever see a 1, we don't really know what it is. So we can do a logical AND of all these locations at read time to then figure out what was the value. And then the third approach was more traditional. It's using error correction codes, Reed-Solomon-Berger codes. So throwing computation at the problem rather than throwing just writes to memory at the problem. Yes?
Good question. So at this point, you're assuming that doing 2 writes at low voltage consumes less energy than doing 1 write in high voltage, right?
It's all about the workload.
Hoping for this, right?
I'm sorry?
This is something that we should hope for, right? Because if 2 writes in low voltage consumes more power, then there's no point.
Well, it's actually slightly more complicated than that. So what you're pointing out is what happens if our error recovery mechanism is really it costs a lot of energy all the time. That would be bad. So the good news is errors are pretty rare. So we don't usually need to use our error correction mechanisms. But when we do need to use the error correction mechanism, the question is, well, is it a small, reasonable cost, or is it such a huge cost that it's going to make the whole process pointless from the beginning? And that depends on the workload. So it's going to depend on whether you're write-bound or something else bound. But the good news is most workloads do actually work out for this kind of scheme.
And isn't it also the case that sometimes you don't have a choice? You're working with low voltage.
Exactly. Thanks for bringing up that point. So there's 2 different regimes you can think about for low power. There's low power because you're trying to save power, and you have chosen to set a constant low voltage to make your device last longer. But the other regime is you've got this energy harvesting device and you have no control over your voltage and you have to live with whatever you've got. And that's what we started from. We were given a low voltage and we could either choose not to save anything. In fact, we went so far as to actually store things remotely over the air because it was cheaper to do that than to bring the voltage up higher to write to flash memory. So some really weird things happen at low voltage. Some very strange design decisions. Okay, so now comes to the part where we have beer. So we're going to represent our bits as these beer mugs using negative logic. So here's a beer mug initialized to 0, and here's a beer mug initialized to 0. You can see it has lots of charge inside it. And we're going to use this to illustrate how these 3 different schemes work. So for the in-place writes, again, we're going to do this repeated write. So we start with our memory initialized to 1, and we want to make it into a 0. So we're going to add charge, but at a low voltage. So it's slowly dribbling out, and our bit tender is putting some beer in there. And it might take 1 or 2 or maybe 3 attempts to actually get enough charge in there before it would be interpreted as a logical 0. So this is sort of bending the notion of analog and digital. We're kind of doing hybrid digital analog all at once in order to save power. Now this took 3 attempts. That's not very ideal. That means it would take 3 times as long to do a write. Question?
Just because it's a 0 immediately after writing, does this mean there will also be a 0 10 seconds later when you read it again?
That's a good question. So we have yet to find any errors of that nature where it has flipped to a 0 and then flips back on its own. Now that's not to say it cannot happen. I'm pretty sure there's some way for that to happen, but the only good news is we haven't yet encountered it. All right. So with that kind of scheme in mind, this sort of feedback loop of keep writing, rewriting until you get the bit you want, you can imagine, so we got on the x-axis the number of attempted sequential rewrites, and then the error rate after that number of rewrites. If this approach is to work, we would expect sort of a quick drop-off from to a very low error rate after just a few writes. And if it doesn't work, well, we'd see no change. So the good news is, at all sorts of different voltages, you'll very quickly see a reduction in your error rate. So already at 1.87 volts, if you do 4 in-place writes, you're going to eliminate pretty much all of the errors. So you could actually have just a static routine with no feedback that just does 4 writes. And you'd virtually be certain to have no errors. If you're willing to have slightly higher voltages, which means you wouldn't get the same energy savings, you can get much higher reliability. So here, after just 1 write, at 1.9 volts, we didn't get any errors detected in these many trials. So there, you can kind of think of this feedback loop as just an insurance policy that we never needed to execute. That's the ideal case. We get really, really close to that wall where error starts to happen, but we never actually hit the wall. So that's our best case scenario. The other approach is we call multiple place writes. So this was in collaboration with Andrew Jang, who's been here before to speak on rank modulation and multi-level flash cells. So here we're going to show how to do multiple place. So imagine you have 2 different bit locations, and in order to do writes, you have to write to 2 locations. So here you can see that we've written a 1 there and a 0 at the bottom, and because we didn't actually get enough charge put into the Texas mug, so I'll make fun of Texas. And then all you have to do is, at read time, do a logical AND. Because of this asymmetric error, you do the and you'll get the actual value. So as long as one of the bits was written correctly, you will read the correct value. We thought this would have worked a lot better, but it was nowhere near as competitive as the in-place writes. And my intuition on why this is the case is this particular mechanism does not exploit the accumulative behavior of flash memory. And so the accumulative behavior really helps out the in-place writes, but it doesn't help out multiple place writes, unless you combine them.
It also seems like flash memory is more homogeneous than you might have expected. It surprises me.
Yes, I thought I would have seen much more variation, but none was detected, nothing significant. I'm not even going to talk about the error correction code with Reed-Solomon-Berger codes because it was an order of magnitude or 2 worse. It just turns out there's so much computation involved that basically you had to pay an upfront fee to do the error correction before the first write, and you might never need that error correction. And therefore, you're always paying this penalty whether or not you had an error. So we found that this feedback loop was much more effective because we only paid for an error when there was an error. Okay. I should move on since I'm running out of time. So I'll just do a couple comparisons. So those were, well, just to explain the difference between in-place and multiple place writes in terms of time and energy consumption, they were pretty close. And because they're so close, it's almost obvious that you want to use in-place writes because it uses less space. So if you were to use multiple place writes, you would have a minimum of a 2x increase in how much flash memory you need to use to get the same job done. So at the moment, we see no reason to use anything other than in-place writes. Moving on, so micro benchmarks. Let's compare doing these in-place writes at a low voltage versus just the standard approach if we were running at a high voltage. So there are no real benchmarks for this yet, so we had to come up with our own. So we're going to think about things that are sort of read intense and things that are write intense and combine them. So we've got 4 different environments we're going to run in. The bluish colors represent our experiment, our in-place writes at different voltages. And the yellow, orangish ones represent the standard world. Different microcontrollers have different thresholds for writing to flash. So the first thing we're doing is the RC5 Block Cipher, which obviously doesn't have a lot of storage. It's mostly computation. So you can see that if you were to pay for the ability to have the potential to write to flash, you are proportional with the worst case scenario of energy consumption. This is normalized energy consumption. And if you were to make it sort of more opportunistic, using Half-Wits, you can save 30 to 50% just on your energy consumption. The difference between the darker and the lighter color is just how much reliability. The darker one, there's a potential for getting an error, small potential, and then the lighter one, we have yet to find any errors. So it depends if you would accept having any kind of write errors. The retrieve workload is very similar because there are no writes going on there. Again, we make it proportional to the workload. The bad news is storing is sort of the worst thing you can do. So I think this was related to the question about what if it takes more energy to store. Yes, it takes more energy to store using this technique. But I claim, so what? So if you had a write-bound workload, every single cycle was a write to flash memory. Yeah, you would see about a 50%, it'd be twice as bad as using the original scheme. The good news is most workloads are not of that nature. Your smoke detector is doing other things than writing to flash memory. And in fact, one manufacturer we're working with gave us a device where they do a 1 byte, I believe it's a 1 byte write to flash about every 5 seconds. So there we're talking a huge ratio in terms of how much non-writing they do. But they pay for writing the whole time. Okay. So the hypothesis is that this low voltage writes in the Half-Wits regime will be much better than the high voltage system for typical workloads. So I'll just give you one workload, and that is of a typical sensor networking monitoring application. So here we're going to read 256 bytes of accelerometer data, and we're going to compute some rather simple statistics and then store that aggregated information to flash memory. And keeping it pretty high level, we were able to get about a 34% energy savings. And again, it's because we exploited this cumulative property of the flash memory. We're able to drive that voltage much lower, get pretty close to the actual safety margin rather than some artificial spec that sets a very high safety margin for writing to flash memory. Here's some raw numbers to just let you think about how things are actually working. If you're working in the standard model at 2.2 volts, to do that workload I just talked about, we measured 410 microjoules. This was measured by looking at the drop on a capacitor. But if you were to use our technique for in-place writes at 1.9 volts, we've yet to encounter an error in that regime, and the energy consumption was only 300 microjoules. So pretty significant savings with no penalty for errors. Now, let's say if you take the approach of errors are okay. There are many applications that are okay with errors. Think about like UDP for storage. If you don't mind dropping down to 1.8 volts, you might get an error after 2 writes. And if that's okay, every now and then you get an error, you can still have even additional savings down to 270 microjoules. But for this reason, if you do care about having sort of perfect data, we found, at least for this particular microcontroller, 1.9 volts is sort of the sweet spot to get things to work well enough before you hit the curve. Okay, there are all sorts of other little improvements you can make. One is kind of fun. If you have data that's always filled with a bunch of zeros, well, maybe you should flip all your bits. So if you have a signed bit, just store the complement, and it'll actually take less energy. And it'll take less energy because you're less likely to have errors. This comes up in EKG data, for instance. If you're storing medical data, you're going to see a lot of zeros. And you can also do compression, things like memory mapping tables to basically have codes to reduce how many zeros you need to write. So to summarize this approach for flash memory at low voltage, it's this regime where we're trying to make our energy consumption proportional with the workload rather than the worst case. And microcontrollers today are basically being abused for cost and manufacturing reasons. They run at a much higher voltage than necessary. Our abstractions are forcing us to do this. So we basically violate the digital abstraction in order to save energy, and we're able to actually bring back some of that reliability through these error correction processes. We are actually considering some commercialization of this. I'll just say that our commercial version of this we call Smash Memory. It's smarter flash. Sounds a lot better than flarter. But you can start to think about if you use this Half-Wits regime you can actually reduce your manufacturing costs because you can now live with components that are higher variable. Oh, you had a resistor that was 5% versus 10% variable. Well, now you can use the ones that are crappier and still get away with it. Smaller batteries. And you can make the device smaller, way less. And also you can make it greener because there are fewer chemicals going into the environment as you're scattering all these things around. And I think I'll just leave with, there's a lot of devices out there that could benefit from this. So we just, I had Negin working with a number of undergraduates, and we called it basically looking for 100 microcontroller products in 100 days. And we did all sorts of power measurements to figure out what the microcontrollers were doing and what they could do. And there's a lot of waste out there. I think I'll just say. Okay, so that's Half-Wits. So, oh, was that a question?
Sorry. Some of the things up there are funny.
Yeah, it's pretty funny what's there.
I actually have a question.
I have some stories about how I got some of this.
You talked a lot about writes, but you didn't touch much on erasures.
Yeah. So,
Where does that fit in?
at the moment, it's just a Turing machine with an infinite tape. So I'm assuming we don't need to do erases right now, or that occasionally, because we're working with energy harvesting devices mainly, we assume occasionally we'll have these sort of happy power seasons where we do have a lot of energy and we can do sort of an erase of everything that's not being used. That might not be the case in all applications. Negin, did you have any comments on erase?
And more than that, we never saw any errors because of the erase. So like when you're doing writes, you get errors at low voltage, but you don't get any errors for the erase operation.
Even as the memory wears out and it gets harder to purchase?
At that point, yes, but during the useful lifetime of the device, you don't get any errors.
And does that require a higher voltage?
No, just
the same.
I think G in the back first.
So it seems to ignore the frequency scaling. If you run instead of at 4.4 volts, but when you clock the frequency a lot higher, you're going to finish your job much faster and save energy that way.
Correct.
Right. Any comments, or this?
There are a couple of comments.
Clock them?
I have a couple comments about frequencies, choosing the appropriate frequency. One is no comment, and the second one is the workloads you see on these kind of devices are not your typical workloads that you would have on a desktop or on a node in a data center. They tend to be doing a lot of sampling, for instance, and you could speed up your clock, for instance, to get more things done. Whether you need that granularity or not is not clear, but.
So the bottleneck is not at the compute part; was rather somewhere else. That's what you're saying.
Typically, the bottleneck is the storage, how much you can store, because the storing to flash memory is an order of magnitude worse than CPU, usually. Do you have anything to add?
We are trying another approach. We call it a slow write. We just slow down the clock for the flash memory, and we write to the flash memory, and the errors drop pretty much. It's much better than just writing at the same.
So there are different ways to get the similar effects. Jakob.
You mentioned flash in fire alarms to settle insurance company lawsuits. What do the fire alarm lawyers say about using Half-Wits?
I think it's good motivation. I think it may be a struggle to actually have that work in a smoke detector in practice, because they have to pass UL inspection, and anything that involves high criticality has huge safety margins. So for instance, although the battery is rated for X years, they only actually advertise it as X over 2 years in order to get their safety rating. So there could be some uphill battles on that. But I think this is the kind of case where there are certain things in place that don't necessarily, certain policies in place that might not make sense. And there are trade-offs, but we can quantify those trade-offs.
For a fixed reliability, suppose you were given a reliability target,
Okay.
99.9% or 95 or whatever, and you could set the voltage as you liked. What would be the ideal? Because my intuition is you'd set it just above that that cliff, and then not do the multiple writes.
Right. Well, there are a couple complicating factors. So first of all, static or dynamic, I'll just fill that in since you asked the question earlier. I think you could do a lot more with dynamic. So if you had errors, you could suddenly, if you have control over your voltage, you could choose a higher voltage. But if you don't have control over your voltage, all bets are off. You don't have a choice anyway. Let's see how to address that. I think it's going to be tricky to address because, as you saw in the earlier slides, even the same chip from the same family has a very different cliff. So you could pick a voltage, but it might be different for the other chip. So you could, what I would recommend is you profile, say, 50 or 100 chips, and then just take the maximum value. Say, well, that seems to be, according to process variation, that's about as high as we'd ever get. Set the threshold there, and that's probably a good static. You wouldn't want anything more conservative than that. There's no need to be more conservative. Unless the chip itself changes and remains the same model number. So if you're a company making 1 billion widgets and you always use the same chip, you could do this, unless your manufacturer of the microcontroller changes its behavior without telling you. Then you'd have to adjust on the fly. Okay, so I'll just wrap up with a couple other weird things we're doing in my lab. So one thing we're doing in trying to get these embedded devices to work well is we're handing out implantable medical devices, not for human use, but if you're interested in using medical devices for your research, come talk to us. We're loaning these out. They're from patients who didn't need them anymore. And so for your homework, besides that, you can start to think about all the interesting problems in this space of very, very low power computing. There's interesting hardware issues like what can you actually move off the chip to save energy? There's some interesting circuitry problems or just memory choices. There are all sorts of interesting options available. Most of us use flash memory today, but phase change memory and ferroelectric RAM and all these other technologies are coming along with different kinds of error properties. Some that may and we believe will work well with this Half-Wits kind of model. And then on the OS and the PL side, there's lots of fun things to do, like with task scheduling, compile time optimizations. I think it's sort of a fertile ground where not a whole lot yet has been tried. And there are probably some really cool ideas from the 60s, 70s, and 80s, maybe even things that were used on punch cards that don't make sense anymore, but might make sense now because we're going so low power. If you want to learn more, and if you don't want to keep repeating your computation, or our computations, you can go to our website, our Roman Empire, spqr.cs.umass.edu. And that's all I have for today. So I'd be happy to take any questions now or offline, but thanks for coming.